Hello, I'm Sejin Park. Today I'll be presenting our ICCV 2025 paper, Interpolation Mixing Look-Up Tables for Image Super Resolution. Super resolution has been a long-standing research topic, both before and after the rise of deep learning. In addition to conventional super resolution, there has been steady research on efficient super resolution as well. So why do we need efficient super resolution? In practice, super resolution is often performed on edge devices. However, edge devices struggle to handle the heavy computation and large model sizes required by typical super resolution networks. To address these limitations, previous research present lookup table-based methods. The idea is to map the input and output pixel values of a neural network directly to the input and output of a lookup table. By doing so, super resolution can be performed without neural networks. As shown in this table, this approach achieves remarkably fast runtime and very small storage size. However, is this real-world scenarios? As you can see, when we perform super resolution, we often zoom in and zoom out. It means we need arbitrary-scale super resolution. So original lookup table approach comes with two major limitations. At the first, a separate table is required for each scale factor. Second, because of the lookup table structure, it can only store integer scales, which means fractional or real-valued scales cannot be supported. Of course, other directions have also been explored. For example, implicit neural network-based methods have been proposed to achieve arbitrary-scale super resolution. However, such approaches come with extremely heavy computation and large storage requirements. And another approach has proposed mapping a single kernel into a lookup table in order to apply different Gaussian filters. However, this method suffers from limited representation capacity, and its parameters are fixed regardless of the target scale factor. That is a fundamental limitation. Let me explain proposed method. First step is IM-LUT training. In here we set K3. The low-resolution image is pre-upsampled using the three interpolation functions. Next, the scale factor is encoded and passed through convolution layers and transformed into a scale vector. Meanwhile, the input image is fed to another convolution layers, and its output is multiplied by the scale vector. This process produced the weights corresponding to each interpolation function. Then, each weight is applied to its corresponding interpolation method to perform upsampling. After that, we mix the results to generate an image that is upsampled to an arbitrary scale. Finally, to recover high-frequency details, the image is refined using a refiner. The training is performed by a traditional L2 loss and a guidance loss that we presented. Now let me explain how we apply the guidance loss. We first prepare images that are upsampled using each of the interpolation functions. For each of these images, we compute how far it is from the ground truth image. These values are then passed through a softmax function, so the output denotes how suitable each function is for each pixel. In other words, it can be interpreted as the optimal mixing ratio. This pseudo-ground truth is then used to supervise the network's weight map with an L2 loss. Now the training is complete. Once the training is finished, the all network is converted into a lookup table. As a result, we can perform arbitrary-scale super resolution in a neural network-free manner using the converted lookup table. For more details, please refer to our paper. Next, that is experimental results. Here NLC means that we mixed three interpolation functions, nearest neighbor, bilinear, and bicubic, as you can see from the figures and tables. Mixing multiple interpolations achieves a much smaller size and lighter calculations while still providing strong image qualities. Furthermore, we observe a more favorable trade-off compared to methods that only support fixed scaling factors. In addition, we confirm that mixing 4 functions produces better image quality than mixing 3, and 3 is better than mixing just 2. Next is the PSNR table. Only use one lookup table. And these are the visualization results. As you can see, our method produces images with better visual quality. Finally, this is the video result of our arbitrary scale super resolution. Thank you for your attention. If you have any questions about our paper, please feel free to contact us through the QR code. Thank you.